program. Currently, he is working as co-PI in submarine groundwater discharge network project funded by Ministry of Earth Science. Topic of today's session is groundwater occurrence distribution and management and related to groundwater modeling with its application of MIAI and DL. So, sir, over to you.
Thank you, Priyanka. And uh, okay, so I'm going to start about my presentation. So, shall I share my presentation?
Yes,
Am
sir.
I audible?
Yes, sir. Yes, sir.
Okay. Slides are visible.
Yes, sir.
Okay. So, good evening, everyone. So, today presentation is about groundwater, its occurrence, distribution, and management. So in today's presentation, I will discuss about hydrologic cycle, importance of groundwater and distribution, how groundwater distributed within the earth surface, occurrence, how groundwater occur within the geological formation, management. So why management is required? What are the different steps we need to take for the sustainable management of groundwater? So let's start with hydrologic cycle. So hydrologic cycle, it seems to be very complex, right? But let me tell you, hydrologic cycle is one of the important cycle in our Earth system. Along with hydrologic cycle, other cycles are there. That is carbon cycle and nitrogen cycle. They are very much essential in our system for sustainable development of life. So hydrologic cycle is also known as water cycle. Okay, so water cycle means that describe how water moves from ocean to atmosphere, then atmosphere to land, and from land to ocean. So there is a circular movement of water in between ocean to atmosphere to land, and land to ocean. So consider ocean as a starting point, as ocean is a vast reservoir of surface water. So what happens in this hydrologic cycle? Water evaporates. Okay, water evaporates and reach to atmosphere. So that evaporates means through this evaporation process. When water reaches the atmosphere, so water vapors, okay, that uh, taken towards the land side, and this water vapor, when cools down, it reaches to the land surface with with form of precipitation or snowpack. Okay, so when it reaches the land surface, then what happens? Then distribution occurs. So that precipitation which reaches to the land surface, distribution occurs. So some part of this precipitation goes on the surface, and that is known as surface runoff, goes to the different river system or lake system or different type of pond. So that is surface runoff, and some part of this precipitation goes below the earth surface. So when it goes below the earth surface through this infiltration process, that consider as groundwater. So here groundwater recharge takes place. That means some part of precipitation goes below the earth surface. Okay, this is the earth surface. When it goes down the earth surface, then it is known as groundwater. Remember, one is surface water, another is groundwater. So surface water basically what surface water we can see it in with our naked eyes. But when we talk about groundwater we cannot see through our naked eyes. Means this is invisible water resources, whereas surface water is visible water resources. We can see the surface water, but we cannot see the groundwater until we explore it. Okay, so then another part of precipitation, that water lost due to the evapotranspiration process. So why I'm talking about all these things? Because our water generally when precipitation reaches the earth surface, how it distributed in different form. Okay. Then finally, what happens? It when it goes to the surface water, then finally it reaches the once again ocean. So that means discharge takes place. So what amount of water generally goes to the surface water or river system through runoff, that once again goes to the ocean. Okay. So similarly, some part of precipitation that goes below the earth surface, and that form the groundwater, that also uh, flow through the aquifer system and reaches the ocean. So that when it reaches the ocean, that is known as groundwater discharge, or that is basically known as submarine groundwater discharge. So this is the overall things. So hydrological cycle, that is basically what we try to understand through a hydrologic cycle, that movement of water from ocean to atmosphere, atmosphere to land, once again land to ocean. Okay. So now the thing is, where is Earth's water? So as you know that Earth is known as a watery planet. Watery planet. Why watery planet? Because Earth is 71% of Earth is covered with water, and the rest is covered with land. So out of this 71% of water, 96.5% of water is is in form of ocean, which is very saline, and the rest 2.5% is fresh water. So being a human being, you know, we cannot use this saline water. We only depend on the fresh water for our household purposes. So once again, you see this fresh water once again classified into three different form of fresh water. One first part is glacier and ice cap. That means our fresh water, that is in form of glacier and ice cap. It consists of 68.7%. Then groundwater. So groundwater we have 30%. Okay, and surface water and other fresh water we have 1.2%. So this is the thing. Means glacier and ice cap, we cannot tap this water. Okay, for our using purposes. But groundwater, of course, we can tap this water, and we can also use this water, and surface water also we can use. So out of this surface water, once again it has been classified. So you see this surface water, basically you see focus on the river. Okay, so out of this 1.2%, only 0.4%, 0.5% is river. So as now I said that river is visible source, so we can see it, whether there is a contamination, whether there is a depletion, we can see in a river. But in groundwater we cannot see, because it is an invisible water resources. But we rely on groundwater more rather than river water, because of it is fresh in nature. So this diagram, you can see this diagram. What happens uh, when we have groundwater? So people, people or the population grows. So when there is a population, so that means there is more demand of water. When there is more demand of water, that means we rely groundwater is more. So then here you can see this Rajasthan side. So Rajasthan, of course, this Rajasthan, as I told you, in hydrologic cycle, one component is very important, that is precipitation or rainfall. If there is no rainfall, that means there is no recharge will takes place. So there is no recharge means there is no groundwater. So here you can see this Rajasthan, you can this is arid climate. Arid climate means there is less rainfall. So when there is less rainfall, so less groundwater recharge takes place. But due to increase in population or population growth, so we depend on groundwater, and we start exploring groundwater, or withdrawal of groundwater basically taking place in this region. So here you can see this groundwater level goes below the uh, uh, let's say 15 meter. And here you can see Punjab area also you see the declination of groundwater level. So this declination or decline of groundwater level is due to the over pumping of groundwater. Means we there is less recharge, but we are extracting more groundwater. So there is a declination of groundwater level takes place. So that's why groundwater is so much important, because yeah, now every means when you start some home, means construct some building, you start rely on groundwater, you depend on groundwater, you do borewell, and you extract more groundwater for your household purposes. So that's why what happens, gradually the groundwater level declines or decreases. So distribution, and here I want to tell you that different type of waters are there. Means here you have different type of water is there. That is, we can say genetic type of water, genetic type how this water originate. So juvenile water is new water. In new water means when there is a rainfall or precipitation occurs, when it reaches the land. So when it infiltrates through the earth surface, goes to the aquifer, that is fresh. And when this water has a residence time is less, then it is called juvenile water. Then comes to magmatic water, meteoric water. So let's what is meteoric water? Meteoric water means that is atmosphere water. We can call it as a rainwater. So rainwater is the common water, and main source of groundwater is rainwater. Okay. So through rainwater, this groundwater recharge takes place, and from this groundwater, when we this groundwater goes from earth below the from earth surface to below the earth surface, then depth wise it goes below. So that means after some years, or that earth, uh, due to this precipitation, that recharge takes place, and after some years what happens, that older water which generally gets trapped within the sediments, we don't use it, that becomes connant water. Connant water means sedimentary, means old water. When magmatic activity, due to magmatic activity, which water generally generate, that is called magmatic water, or volcanic, or you can say volcanic activity. From due to volcanic activity, some water generally comes up, that is called magmatic water. And metamorphic water basically, in geology or in our science field, we generally consider this, the water present in some minerals, means that is hydrous mineral like mica, clay. These are the hydrous minerals, these are present, or we can call this metamorphic minerals also. Then oceanic water, finally I told you, oceanic water means after all this water, and all this water, that is magmatic water, metamorphic water, and connant water, meteoric water, after sometimes they get discharged into the ocean. So you means you aware of this thing, why ocean water very saline? Because of this thing, because of we have surface water, means river system, we have groundwater system. So all this water from river system and groundwater system that discharge into the sea. So lot of sediments and lot of minerals they generally carry when they flow through their channel and discharge or deposit into the ocean. So that's why this ocean water is very saline compared to other type of water. So we discuss about we right now I told you that below the earth surface we have groundwater. So this is the ground surface, or you can consider as earth surface. So below the earth surface we have two different zone, that is zone of aeration and zone of saturation. In this diagram, I just try to tell you that how this groundwater vertically distributed. Okay, so in zone of aeration and zone of saturation, in zone of aeration we have a soil water zone, intermediate waded zone, capillary zone. So this zone basically, below the air surface we have different sediments, or we can say different particles. Within these particles we have some pore spaces, and when these pore spaces are partly or partially filled with water and partially filled with air, then it is called as zone of aeration. Okay, so the below the zone of aeration, another line is there, that is water table. So below water table we have zone of saturation. So here we have pore spaces that is partly filled with water and partly filled with air. But in case of zone of saturation, these particles or these pore spaces are filled with completely water. So that's why it is known as zone of saturation. So water table is the uppermost part of zone of saturation. So below water table we have groundwater, that is also ferritic aquifer. Generally we call this ferritic aquifer, or we call this unconfined aquifer. We'll discuss in later slides. Then what is aquifer? So finally the thing is, in previous slide also I have mentioned aquifer. So aquifer is a geological formation which can hold water. Okay, and which can also yield some adequate amount of water. Means adequate amount of water means which can yield that sufficient water which can be used for our household purposes, or for our drinking water purposes, and other household purposes. So this diagram is showing a lot of things. Means yeah, you can see this. First, start with unconfined aquifer. So here we have unconfined aquifer. You see aquifer A, that is unconfined aquifer. Why it is unconfined aquifer? This aquifer, it is below this aquifer we have one confining unit, that is known as aquiclude. So in aquiclude, basically what is aquiclude? It is a impermeable unit. So there is no flow. Means when if in aquifer what happens, there is groundwater flow takes place. Okay, in unconfined aquifer what happens? One part, if this is the aquifer, that lower part is impermeable zone, that is known as aquiclude, and the upper part is open to atmosphere. So there is no confining unit in this unconfined aquifer. So that is called unconfined aquifer. And below this unconfined aquifer, we have confined aquifer. Confined aquifer means it is bounded by two impermeable unit. Impermeable unit means this aquiclude are the impermeable zone or impermeable unit. These are the impervious. Through this layer, water cannot move. Okay, so that's why it is aquiclude. Okay, but in aquifer, pore spaces are there, and that's why water can move, and we can also easily access this water. So then another part is paused aquifer, that I will discuss in next slide. Then we how to tap this water. So Now we discuss about groundwater. Groundwater is an invisible water resources. So how to tap this water? We have to do borewell. So this is the borewell. So first this sea borewell we have borewell up to confined aquifer, that is aquifer B. Okay. Then another we have borewell, that is borewell A, that is tap. We have only tap for tap to unconfined aquifer, and another borewell, that is B, is also tap to confined aquifer. So there, these three borewells we have done, means here it is showing that three borewells are there, and three borewells they have individual characteristics. As you can see, B borewell. So B borewell is flowing well. Flowing wells means when we do this borewell, the water comes automatically. We need not to put any submersible pump to take out this water. It automatically flows because of this piezometric surface or potentiometric surface. So what does mean by this potentiometric surface? Means when hydrostatic pressure is more than the atmospheric pressure, then this autoflow condition we generally uh, uh, found in field. But in case of when this is there is also hydrostatic pressure, but hydrostatic pressure is not more than the atmospheric pressure. That's why there is no non-flowing, that is not it is not an autoflow condition. Okay. And unconfined aquifer, in unconfined aquifer this is water table. In water table, unconfined aquifer we have water table only, because there is no confining unit below this aquifer and above this aquifer. So this is unconfined aquifer. So we have water table. Water table is the surface or imaginary line on in which the atmospheric pressure is equal to the hydrostatic pressure. Okay. So these are the total aquifer system. So when we need to understand what are the different aquifers present when we start some means we start constructing our building or any building. So when we require water, right? So for this requirement we need to understand what type of aquifers are present, or is there any aquifer is present or not. So accordingly we have to plan to build our building or construct our home. Okay. So I discussed in previous slide, that is paused aquifer. Paused aquifer means it is a isolated type of aquifer. Isolated type of aquifer, and it's when this is the ground surface, you can see this is unconfined aquifer. I told you, and this is water table. Paused aquifer is a very small type of aquifer. What happens, this is the confining unit, and within this is confining unit, it is basically you can say uh, tap some tapping type of, or some sediments are there, and within the sediments the water get deposited. So that is known as paused aquifer. So sometimes we use leaky aquifer, because the aquitads basically here what we have seen, one is aquifer, one is acutad, one is acutlude. So aquifer is it is a geological formation which can hold water and yield water, sufficient amount of yield water, and which can be usable. Okay. And acutad is semi-permeable, means water can flow through this aquifer system, our aquifer system. Very less amount of flow will be there, which cannot be means explore or tap for household purposes. Or fluid is it is impermeable, so there is no pore spaces within this. Fluid has pore spaces, but it is impermeable, means water cannot move through this pore spaces. Okay. Then occurrence of groundwater. So occurrence of groundwater, it basically depends upon what type of, means rock types are present in the below the earth surface. So here we have India map, and in this map different type of aquifer systems have been mentioned. You can see this. This is Ganga basin. Though this is a Ganga basin. Ganga basin basically consists of alluvium, and then other parts you see, you can see Odisha, then Telangana, and some part of Jharkhand. So these are basically hard rock terrain. So there is a difference between alluvium formation and hard rock formation. In alluvium formation, what happens? The sediments are basically unconsolidated. When there is unconsolidated formation, that means the pore spaces are more, and when pore spaces is more, so water can store within these pore spaces. But in case of hard rock, the rocks are very compact and very crystalline. So here I have this is mentioned how this India, means our India, is classified on the basis of different rock group. So some part is crystalline, some part is volcanic rocks, some part carbonate rocks, some part clastic rocks. Okay. So when we talk about crystalline rocks, so that means it consists of non-volcanic, igneous, and metamorphic rock. So example of these rock is granite, gneiss, schist, slate, and phyllites. So these are the rock which are very hard rock and very massive, and so the chances of groundwater in this type of rock is less. But however, there is some chances sometimes groundwater occurs within this crystalline rock. If some fractures is present, some weathered zone is present, then groundwater can occur within this crystalline rock. Then volcanic rock, we have basalt, andesite, and rhyolite. These are the some example of volcanic rock. In volcanic rock, what happens? Some vesicles, basically basalt, some vesicles are present, and within these vesicles, the water generally gets trapped. And when this water gets trapped, then then groundwater or potential of groundwater we generally found in this uh, basaltic rock, but fractures should be there. So without fracture, this groundwater flow cannot be possible. So fractures should be there. So these fractures basically fractures within this volcanic rock or crystalline rock are considered to be the potential zones. Then carbonate rocks are very good example of groundwater means depository, because these are limestone and dolomites. These are very they are chemically precipitates rock, and they can easily react with water and give some solution structures. So this within these solution structures or fractures, this groundwater can occur. So these limestone and dolomites are sometimes or mostly they act as the potential aquifer system. Then comes to the clastic rock. As I told you, that is the Ganga basin. Ganga basin, that is unconsolidated sediments. So unconsolidated sediments means there is no binding particle within this sediment. So when there is no binding particle within the sediments, that means many pore spaces are there, and these pore spaces are interconnected or intergranular pore spaces. So these are this due to this intergranular pore spaces or fractures, so these are considered to be a highly potential zone for groundwater occurrence. So I talked about the different intergranular pore spaces. So pore spaces, when voids within a rock Generally, these voids or pore spaces are filled with water. I told you, in below the saturated zone, the pore spaces, all the pore spaces are filled with water. So porosity is one of the fundamental criteria or fundamental parameter which can tell you whether this geological formation can accommodate water, groundwater or not. So and that this porosity also helps this groundwater to movement. So provided these pore spaces should be interconnected. So if pore spaces are there and they are not interconnected, then groundwater flow or movement cannot take place. So we have two type of porosity, or that is primary porosity and secondary porosity. So porosity, primary porosity means when this porosity form or pore spaces form during the formation, when rock, during the formation of rock, when rock form, at that time that pore spaces develop within the rock, then that is called primary porosity. So when after the formation, some pore spaces develop within the rock, that is called secondary porosity. So like fractures and solution structures, these are the secondary porosity. These are formed after the formation of rock. Okay. So how to calculate this porosity? So total volume of voids, and here you can see different type of porosity are there. These are the this is the porosity. Here pore spaces are there. Here also pore spaces are there, but these are not interconnected. Okay. So here pore spaces are there, but it is not interconnected. Here also you see pore spaces are there, but within the spaces some materials, some matrix are there. So compared to this, it has less uh, pore spaces. Here also, so these are the primary porosity. When these porosity develop during the formation of rock. But in case of this, you can see these pore spaces are interconnected. So when pore spaces are interconnected, then this is considered to be as a means good groundwater flow or potential zone in with respect to its effective porosity. So effective porosity means that is the interconnected pore spaces through which this fluid or groundwater flow can take place. So this is porosity. Porosity are described in percentage. We have unconsolidated materials. So in unconsolidated materials, you see the porosity varies from 25% to 70%. But in case of solid rock, like I told you, that crystalline rock or igneous rock, metamorphic rock, you see the porosity is very less when it is in unfracture condition. So there is no pore spaces, no secondary porosity. So when there is no secondary porosity, so that means very less, means let's say 5% porosity is there. When this volcanic rock or igneous rock get fracture, then porosity is more. So from 5% to it varies to 50%. then then poorly sorted abundant sediments, I told you, when poorly sorted means there is less porosity, and when well sorted, when these granular or grains are well connected with each other, then these are well sorted. Then well sorted means porosity is more. Here you can see the porosity is more. Okay, this is ill sorted. Okay, this is well sorted, so porosity is more. But in ill sorted, poorly sorted, but there is effective porosity is there, so that basically help to flow the groundwater through these interconnected pore spaces. Then we have secondary porosity. These are the secondary porosity. These are developed after the formation of rock. These are the fractures or solution cavities. So solution cavities in limestone, dolomite, these are basically secondary porosity, and these are considered to be a potential aquifer zones. Similarly, fracture rocks are also in hard rock terrain like in Jharkhand or in Odisha. We have Keonjhar. So these are the hard rock terrain. In hard rock, fracture should be there. If fracture is there, then we have so there is a chance of groundwater potential groundwater zones. So now how this groundwater flow. So Darcy, one in 1856, a French hydraulic engineer, he actually derived this equation. So how he derived this equation? He considered this aquifer, and this is a porous media. So he consider this aquifer is a porous media, means groundwater can flow from one end to another end. Okay, so here we have one hydraulic head, that is let's say here higher hydraulic head, and here is the hydraulic head is less. So hydraulic head basically it is the water level, but above the mean sea level or some reference plane. Okay, so when we take this water level above the mean sea level, then it is considered as hydraulic head. Okay, so this is one point. This is A point where hydraulic head is more. B point where hydraulic head is less. So, what Darcy suggests? Darcy suggests that Q is the discharge. So, how much groundwater or how much groundwater or volume of groundwater basically flow, or volume basically flow this porous media. So that is calculated by, or that is and that Darcy wanted to estimate. So he derive one equation, that is Q directly proportional to cross sectional area, that is A, and directly proportional to the head difference between 2 points, and inversely proportional to the distance between the between 2 points. So that is the head difference, that is HB minus HA, that is del H. So del H by del L is gradient. So basically the Darcy law is Q is equal to K A I K A I. So K is the hydraulic conductivity. Okay, so K is hydraulic conductivity. It is one of the important parameter in the aquifer system. So as this is why I discuss a different type of aquifer, because we want to know the different aquifer parameters. So these aquifer parameters, these are the data. Basically, in this presentation, we more concern about what type of data we are collecting, and through this data, how we can do some groundwater modeling work. So, so first step is acquisition or data requirement is necessary. So how we collect this data? So these are the different process. So here we can see these are the different aquifer parameters, that is transmissivity. Transmissivity basically you can say this is aquifer, this is the aquifer, and when hydraulic conductivity is multiplied with the thickness, then that is called transmissivity. Transmissivity means the volume of water flowing through a cross sectional area of an aquifer, that is 1 feet cross sectional 1 feet into 1 feet cross sectional area and having thickness of 1 feet. So and flowing under a hydraulic gradient of 1 feet, that is basically transmissivity. So in case of confined aquifer, we use storativity, or in case of unconfined aquifer, we use specific yield. So specific yield means how much water actually yields from a aquifer system. Then management and pumping. So pumping. Why pumping is actually how to, because as you know that this groundwater can be extracted through pumping well. So We have here you can see this area, some part of Punjab, Rajasthan, Delhi. So these area are highly, they are extracting more groundwater. That means they use heavily pumping is mainly. We have this area basically heavily extracted area, heavily extracted groundwater area. So this is why they extract more groundwater. They extract more groundwater for their agricultural activity. So you know that now India is a front runner to provide food. So they use more groundwater to to produce these agricultural products. So here you can see this they use number of wells, so many wells from this year to this year, this it is going very drastically increasing the number of wells to irrigate their land, to extracting groundwater from the aquifer system. So that's why what happens, this groundwater level uh, gradually decreases. So what happens in pumping well, we extract, this is one pumping well, and this is observational. Being a scientist or being a geologist, what we do, so when we install some pumping well, we try to see the its influence in nearby area. So we put number of observation wells are there. So this is the pumping well. We extract water from this well. When we extract water from this well, we try to see its influence in nearby area. Like this is one observation well which was tapped to the top aquifer, then another observation well which is tapped to the intermediate aquifer, and final another observation well. So three different observation wells are tapped to identify or to know its influence due to the pumping activity. So these are all this is why we are doing so. So to know how water level is going down due to the pumping, or due to the over extraction of groundwater, may lead to the declination of groundwater level. So to identify this or to investigate this type of condition, we do different type of study. From pumping well also, we try to collect the different aquifer parameters like discharge, hydraulic conductivity, transmissivity. These are some parameters. So after collecting these parameters, then we can do some modeling work. Okay, so that's why. So this presentation is about to what are the different methods we use to tap this or to collect these hydrologic parameters or aquifer parameters. So in this diagram, it is showing that due to the pumping, how the means energy, different type of means how it affects our country, means when we use a lot of pump, diesel, electric pump, and how it affects our country in or you can say output to in form of carbon dioxide, in that way. So, as I told you that groundwater is very much important. So, due to heavy extraction or unplanned manner or unplanned way of extraction of groundwater, any unplanned management of or any there is no proper management of groundwater extraction, or so that leads to groundwater crisis in India. So you can see this. So lot of people in India, they generally face this water crisis. So now we have to manage this. We have already lost a lot of water. Means now we have limited water resources and limited amount of water. So we have to manage, we have to plan, we have to develop some model so that we can predict the water level condition nearby future, or accordingly we can plan or make some policy to save or to protect this water. So this is not only by extracting groundwater. We are not actually we are not deficient. We are not having deficiency in water, but in we have also contamination of water. Means there is deterioration of groundwater also takes place. You will see a lot of in different parts of India, you will there is the population is increasing and they are not able to get the good quality of water, and they are also facing problem to get that adequate amount of water to for their householding purposes. Similarly, here also this is the coastal states. As you can see, this is the coastal states of India. In coastal region of India, what happens? This coastal region of India, or we call this coastal aquifer system. This coastal aquifer, due to heavily extraction or withdrawal of groundwater, that leads to seawater intrusion in this aquifer system. So that means this coastal aquifer system, which are considered to be very fresh, so now they are affected due to the saline water intrusion. So these are the saline water intrusion. So this also creates a lot of problem. So to avoid this situation, to avoid uh, uh, to replenishment of groundwater, to recharge to recharge of groundwater, we need proper plan and proper management of groundwater we have to do, and that can be done through some modeling study. And the next session I will talk about so what type of modeling basically we do to manage or to for the sustainable development of this groundwater. So this is I was discussing about the coastal aquifer system. So this is the different wells. So here we have four wells. So four wells are present away from the coast. These two wells are very close to the coast. Okay, and from among these two wells, one well is very shallow well. Shallow well means it is about 10 to 20 meter the well depth, but another is deeper well, so it is around to 10 meter. So when we are means heavily pumping, general when heavily pumping is done, so what happens, this salt water goes into this well and makes this aquifer saline. So we cannot use this groundwater because of its salinity nature. But in case of these wells which are away from the coastal seashore, so it is not affected by salt water. So how? So when there is, this is the groundwater, fresh groundwater. When fresh groundwater is there, so there is, then it maintains its potentiality, and it gives some pressure to further ingress of ground seawater into the aquifer system. So these are the different parameters I have used for this study. Some chemical parameters I have used to identify how this aquifer systems is affected by the salt water or seawater. So these are the various photograph. These various photograph. This photograph is basically why I have used this photograph. How one geologist or hydrogeologist collects the sample from the field. So in first photograph we have some pond. We here I am collecting the pond sample. In second photograph here we are measuring the infiltration rate. So how much time it will take to means from our surface to down to the surface, how much time it will take to take water goes, how much time it will take when water moves from R surface to below the R surface. So and then we have this is a dog well. So in this dog well we have put some data logger. In this data logger we try to collect the water level by doing some pumping test. So we have used some pump. So we pumped this water for some time, and based upon different time condition, we try to measure the fluctuation of water level, or how much time it will take to goes down uh, below the static water level. So after doing so, we collect some this data, and we plot this data how this aquifer actually responding when we pump water for a specific period of time. Okay, thank you.
Thank you, sir. Participants, we will take a short break of 10 minutes, and after that, we will continue our session. Please stay with us.
Okay. Okay.
We'll start the session from 8 p.m.
8 p.m. Okay.